Sundar Srinivasan to give today's colloquium. So he'll be talking about nearby evolved stars survey. So just to briefly introduce Sundar. So Sundar is currently at IRIA UNAM in Mexico. So I know Sundar from good old days. We were batchmates together at ISC in the same IPHD batch. And eventually he found greener pastures in Johns Hopkins, where he did his PhD. And after that, a couple of postdocs, one at Institute of Astrophysics in Paris, where we again bumped into each other. And then he was in Taiwan in Academia Sinica, and after that he moved to Mexico. So Sundar, over to you.
All right, thank you very much. Thanks a lot for organizing, and thanks for having me over. I know this is probably not the topic that you're used to here. I'll try to be as basic as possible, but please stop me if you have any questions in the middle. I don't mind. So I'm just going to tell you a little bit about the Nearby Evolved Stars Survey, which is a program that we started about 6 years ago. It has since turned into an international collaboration of, there's a total of about 100 scientists around the world. This is only the key players that you're seeing over here. The principal investigator, Peter Shikluna, is an ESO fellow at this point. And we have, like I said, well, we are worldwide. And part of the reason I'm giving this talk in India is to try and get that bit shaded blue as well. So I'm going to tell you a little bit about the collaboration, tell you a little bit about why we care about the kinds of stars we study in this survey. And then tell you a little bit about the initial results, and then talk about how Indian scientists could help us a little bit. One of the things, our overview paper has been published last year, and it's available over there. So, first of all, I'm going to tell you a little bit about the kind of stars that we're interested in. They're called asymptotic giant branch stars. I hate that term as much as you do, probably. Observational astronomers should not be allowed to name things. What are asymptotic giant branch stars? Basically, the life cycle of a star is very sensitive to its initial birth mass. And so in this very nice cartoon here, we have stars forming in a nebula, and then depending on their initial masses, they go through two different stages, two different types of lives. So we have first the sun-like stars with masses up to about 8 times the mass of the sun, which eventually, after they exhaust hydrogen in their cores, turn into red giants. And once they also exhaust the hydrogen, once they completely burn the helium in their cores into heavier elements, they end up as an asymptotic giant branch star. At this point, the size of the star is approximately about an astronomical unit, and that's very cool. The temperatures are about 3,000 Kelvin or so. Eventually, these stars, through some interesting processes, which I will discuss in a little bit, turn into planetary nebulae surrounding a white dwarf or sometimes a neutron star. And eventually this bright envelope is shed into the interstellar medium, where it recycles this material, except now it has heavier elements in it. So it's nuclear enriched material, which is now seeding the next generation of stars. Massive stars have a slightly different and much shorter lifetime. The nuclear reaction rates are much faster, so they burn the fuel much faster as well. So anything above about 10 solar masses or so will eventually become a red supergiant, and then will probably go through a supernova explosion, ending up with either a neutron star or a black hole. Why do we care about these objects? Well, because of the fact that for the very first time, products of the nuclear reactions are being cycled out to the surface due to the giant convective shells that these stars have. Because of the fact that these nuclear enriched materials are finally coming out to the surface, it's for the first time that we can actually detect proof of nuclear fusion in stars. So once they come out to the surface, eventually they're recycled into the ISM, the interstellar medium, which means that asymptotic giant branch stars and red supergiants are the main contributors of nuclear enriched material to the interstellar medium of galaxies, in the form of gas as well as dust. Gas and dust meaning solid particles. So one of the reasons AGB stars are so important is that, well, they're sun-like, which means They're numerous. There are many, many more low mass stars than there are high mass stars. So these are numerous stars. There are many stars in a present day galaxy, for example, which means that the amount of material that they put out in total is going to be very significant. So the main reason I study these stars is that they are significant contributors of dust to present day galaxies. Why is dust important? Dust is solid particles with sizes approximately about a micron or so. Their surfaces have, they're not regular, the surfaces have depressions and dips and stuff like that, which act as adsorption sites for hydrogen atoms to attach for a little bit. That's important because that slows down one hydrogen atom enough for it to increase the cross-section of formation of hydrogen molecules, which in turn are important for the formation of stars. So if it were not for solid dust particles, star formation would take longer than a Hubble time. So this is the main reason. Just as you use platinum in hydrogenating oils, dust is your platinum out in space, making it so that stars can form much faster than they would if there were no dust. Asymptotic giant branch stars form a huge amount of dust because there's many more of them. Red supergiants, each individual red supergiant has a huge amount of mass. So it can, in principle, generate much more dust per star. However, because of these energetic explosions, they also destroy a huge amount of dust. So in their case, we're not entirely sure who wins out, whether or not the dust that they produce actually survives. So we're going to say the jury's out, so it's still okay to study AGB stars.
So when you tell dust, these are material, what materials are?
Everything that is, so in astronomy, one of the jargons is metals. Anything heavier than lithium is a metal. And so these dust particles, I'll come to it a little bit, but the main chemical difference is whether or not they are carbonaceous or oxygen rich. Those would be the two main differences there. So either silicates or carbides of that sort. Yeah. All right, so I'll give you a very rough picture of what's happening deep inside the star and slowly work my way outward. So the core of the star is inert. It has carbon, oxygen, and no longer pressure enough to squish those things into heavier elements. You have these two very thin, comparatively thin concentric shells, first of helium here and then of hydrogen, which are still fusing. So the hydrogen shell is constantly fusing, converting hydrogen to helium, which dumps the helium ash onto this shell here, the helium shell. The helium shell, every once in a while, gets enough critical mass to flash very quickly to 12 carbon. And whenever that happens, the hydrogen shell in it, momentarily stops its fusion. But the helium flashes is what is producing 12 carbon, which was one of the most important nuclides produced in AGB stars, which is eventually cycled out due to this. The entire star at this point is almost just one huge convective cell. So this 12 carbon and other other products are mixed out to the outskirts, about 1 AU, that's the stellar radius, where we have interesting phenomena, partly because of the helium flashes, which are called thermal pulses. This energy, by the time it's transported to the outskirts of the star, results in phenomena like hydrodynamical phenomena like pulsations. So AGB stars are actually long period variables. Their periods are between 100 to about a couple thousand days or so.
Sundar, very nice question. So how do we know that this kind of dynamical processes are happening? So what are the sequences? So like, for example, you're saying pulsations.
Yes. So thank you for the question. Pulsations are easy to observe because so these are pulsations of the actual light as well. So you can observe this in the optical. The amplitudes of these pulsations can be huge. So the luminosity can change by a factor of 10 to the 3 in some cases. So yeah, these are long period variables. So as the period increases, in general, the amplitude increases as well. So the stars with the longest period will be very, very easily visible. So for example, Betelgeuse, you may or may not have seen this over the past year and a half or so. There's been this discovery that Betelgeuse is suddenly dimming. And one of the many explanations that's been put out is that maybe it's about to explode. But another explanation that's been put out, and Peter Scicluna is one of the authors on that one, is that it's just the dust shell. It just recently just puffed out some new freshly formed dust, which is absorbing the starlight, and therefore there's a sudden decrease in. So you can actually observe, especially for the nearest stars, you can observe this at different wavelengths. The shocks and the pulsations, one of the things that they do is they levitate these gas molecules to higher regions where the temperature is low enough that you start forming solid particles. That's where all the dust is forming. That's typically about between 1.5 to about 10 times the radius of the star. That's the dust formation zone. The temperatures here are below 2000 Kelvin and can be down to about 500 Kelvin or so. Beyond this, the densities are too low for the formation of solid particles. So there is a sweet spot, kind of temperature-wise and density-wise, and therefore pressure-wise, where you can form dust. Once the dust is formed, there's something interesting happening here. So these stars, the surface temperature, the effective temperature is about 3000 Kelvin.
When you say dust, what are the lengths?
The size? Yeah. So we are talking about something between maybe a thousandth of a micron, a hundredth of a micron, to about 100 microns or so. Yeah. So these, because the particle sizes are comparable to the peak wavelengths of light emitted by the star, the dust is able to more efficiently interact with the radiation than the gas is. And so once the minute you start forming dust, you have much better radiation pressure. It's more efficiently transferred to the material, and that drives an outflow. So you have, once the dust starts forming, you have an outflow from the star. So the star is, for the very first time, its energy generation and energy loss is not determined by the nuclear core energy generation. In fact, you can empirically show that the luminosities of these stars, the radiation pressure of these stars, is significantly larger than the nuclear burning rate, the energy from the nuclear burning rate. So this is the very first time in the lifetime of the star when this is happening. So because of that fact, because of the fact that the energy loss is much faster, at a rate much faster than the rate of energy production, these stars will lose mass and therefore will eventually, that's how they're shedding their envelope and eventually forming a planetary nebula with a white dwarf in the center. In this circumstellar envelope, there's of course dust, the solid particles I was talking about, but also gas. So how much of it is dust and how much of it is gas? Actually, 200, only about 1% or less of the mass is in the dust. So the solid particles, even though they're the ones driving the mass loss, only constitute maybe 1% of the total mass. So even though they're not very dominant mass-wise, they are the important drivers of the subsequent evolution of these stars. Chemistry. So there was a question about what is the chemistry of the dust here. These stars on the surface start out oxygen-rich. That's simply because that was the primordial composition, the composition with which the area began. It had much more oxygen than carbon because carbon is produced by intermediate mass stars. So it started out oxygen-rich. Yeah.
In nucleosynthesis, are carbon and oxygen kind of preferred compared to nitrogen and argon and amnion and so on?
Yeah, yes, actually. So it just ends up being in that sense. So there's, depending on the average speed of the neutron in the core, you can classify this products into S process as in slow and R process as in rapid. So if your masses are less than about 4 solar masses or so total, then you end up having products which are results of the S process. And carbon-12 is one of the most S process elements, most important S process elements. The nitrogen usually is an intermediate product. So it usually gets converted to oxygen before it can come out of the surface. Yeah. So the reason that initially the surface starts with oxygen-rich is oxygen is one of the R process elements, which, for example, could have come from a previous supernova explosion because the progenitors of supernovae don't live very long. So you could have had a supernova in this region, and then the AGB star eventually took over after 1 billion years. So the surface initially is oxygen rich, but once you start transporting the freshly produced carbon to the surface, you now slowly start increasing the ratio of carbon atoms to oxygen atoms. And the chemistry, which was originally oxygen rich, molecules, oxides and silicates here, changes to carbon rich, and you end up having carbides and cyanides and acetylene, which is an important precursor because it's a building block for more complicated molecules in dust as well. Okay, with that, so this is kind of a primer to what happens inside and what happens on smaller and larger scales. One question we can ask now is, based on this information, what are the wavelengths of light we can use to study various parts of these AGB stars? In the optical, you have a very good idea of what the photosphere looks like. That's where most of the emission from the star is coming, from the actual star itself is coming in the optical and the near infrared. It's at the same region that you get atomic emission and absorption lines, and also molecular absorption lines. In fact, the most evolved AGB stars have so much molecular absorption in the optical that it's called line blanketing. The lines are so close together, they form bands. The bands are so close together, they form this gigantic blanket that completely reduces the optical emission, extinguishes the optical emission from the star by a factor of up to 1,000 or more. And that's probably one of the contributions to this great dimming of Betelgeuse as well. In the near infrared, you actually see the photosphere peak, and you can also make out molecular bands, most importantly, carbon monoxide. By the way, carbon monoxide, second only to molecular hydrogen, is the most abundant molecule in the universe. In the mid-infrared, which is about tens of microns or so, you can see again absorption bands, but for the first time you start seeing signatures of dust, emission or absorption features of either carbonaceous or oxygen-rich dust as well. So the mid-infrared is kind of the only region where I can figure out the chemistry of the dust in these things. And because you're actually now in the mid-infrared, the temperatures that you're probing are about 2000-ish Kelvin, you're actually looking at the dust that is freshly formed, that has just now been formed. It's still very close to the star, has not yet started its way outward. As you move to longer and longer wavelengths, you start therefore probing dust that is colder and therefore older as well. So this way, just by looking at the infrared wavelengths, these 3 infrared wavelengths ranges, you're looking at what is called the mass loss history of the star. The longest wavelengths give you the earliest batch of dust that was produced in these stars. The mid-infrared gives you the nearest one, the latest one as well. So if you can simultaneously get data at all these wavelengths for a given star, then you're actually probing the entire history of mass loss. And it can go up to hundreds of thousands of years, in fact, in the history of mass loss of the star. So that's one reason we wanted to combine all this information as well. All right, so those are the wavelengths at which we can study the AGB stars. Let me tell you a little bit about what we actually have looked at. And your question, of course, is going to be, why am I looking at nearby galaxies? Why haven't I looked at our own galaxy? Well, the answer is on the next slide. So we've done a lot of work on nearby galaxies, starting in the mid-infrared, because that's where we're looking at the freshly formed dust. And it's in the mid-infrared where AGB stars are among the brightest objects in the galaxy, because they're producing huge amounts of warm dust. So these are images from the Spitzer space telescopes. That's wavelengths starting at 3.6 micron up to about 500 micron, but these images only have 3.6, 4.5, 5.8, 8, and 24. So you're going up to approximately 30 micron here. That one is the Large Magellanic Cloud. The Spitzer image was the first one that actually showed for the very first time confidently that the Large Magellanic Cloud has this weird boxy shape. The blue stuff you're seeing, the blue haze that you're seeing, is all the old stars, as in the AGB stars, that don't have any dust. So these are the ones that are peaking at 3000 Kelvin or so. The yellow stuff and the green stuff is a combination of old stars that have a little bit of dust and also young stars that have a little bit of dust. And the red objects here, they're very patchy. Those are the most massive young stellar objects. So because young stars are formed in dust and because old stars produce dust, they look very similar in the mid-infrared. And it's from the patchy distribution that you can tell, okay, this is a young star because it has not yet had time to relax its spatial distribution. So these are star-forming regions here, 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 and maybe there as well. This is Large Magellanic Cloud. We have the Small Magellanic Cloud as well. And this one is the Triangulum Galaxy, which is slightly further away. The good thing about studying AGB stars in these galaxies is, well, you can image the entire galaxy in a few fields of view. The AGB stars are very bright. You can identify all of them. And the distance to each of these galaxies is well calibrated. The thickness of the galaxy is negligible compared to the distance, which means that all of these stars are basically at the same distance from you. And the interstellar reddening, the galactic contribution to the reddening is known, which means you can correct for it and therefore get the most accurate distance to these galaxies as well. What we have done for these objects is once you identify these individual dots and say that they're AGB stars, well, the way we do that is we have what are called Hertzsprung-Russell or luminosity, temperature, or color magnitude diagrams. So on the y-axis, you have something that is a proxy for the luminosity of the star. On the x-axis, you have something that is a proxy for the effective temperature of the star. And once you plot the entire population onto this grid, you see that there are a lot of there's a lot of structure here. So for example, there's this vertical structure over there. Those are just foreground objects in our galaxy, which are at the same color but at different distances. Then you have this little structure here, which is the most massive stars. These are the red supergiants. You have massive oxygen-rich AGB stars. You have intermediate mass oxygen-rich AGB stars. Then you have carbon stars here, the carbon-rich AGB stars. This population here is actually a mixture of chemistries, as in some of them are oxygen-rich, but most of them are carbon-rich. But we don't know which one is which because it's basically a mixture of the most evolved bright oxygen-rich stars and the most evolved carbon stars. But the point is that you can have an observational proxy diagram of the sort and identify candidate stars that you can go study in more detail. One thing we can do with this is, oh, I'm sorry, I should have expanded this out. We can generate spectral energy distributions, which are plots of the flux of the star as a function of the wavelength. Once you have this, it tells you about the shape of how the energy is distributed in the star. You can use that, first of all, if you integrate it, you have the total energy of the star, the total luminosity of the star. So the plot you have here is a distribution of luminosities of two kinds of stars. The blue ones are the oxygen-rich AGB stars, and the red ones are the carbon stars. You can see that the luminosity distribution, the shapes are different. The carbon stars have a much more constrained range of luminosities, between about 3,000 to about maybe 20,000 times the solar value. The oxygen-rich ones have a much wider distribution. That's one reason is that there are very low mass oxygen-rich AGB stars and there are very high mass ones as well. The carbon stars are only formed from the intermediate oxygen-rich AGB stars. So that's why you have this little wedge here. Now, that's the first thing you can do. You have a distribution of the luminosities. One thing you can get out of this is what is the typical luminosity. If I picked an AGB star at random, what's the luminosity of that star going to be? That's something we can calculate. Another thing we can do is, now, if you look at the spectral energy distribution of the star, of the star plus dust, what you're looking at is radiation from the star that has been processed by the dust. So the more dust you have, the more radiation is going to be emerging in the mid-infrared instead of the optical. So that means that there is a correlation between the dust mass in your shell and the flux that you're observing in the mid-infrared, which means that you can work back from the spectral energy distribution and figure out what the dust mass is. In fact, you can figure out what the rate is at which the dust is being lost into the ISM, and that's what radiator transfer models can do for you. You can figure out what the dust production rate is. That's the rate at which dust is being, the mass of dust is being lost. The corresponding quantity for the gas is called the mass loss rate. That's the gas mass loss rate. So I'm just mentioning this because I'm going to use dPr in my some of the plots later on, and that's the dust mass loss rate, whereas the MLR is the gas mass loss rate. Like I mentioned before, there's 100 times more gas than there is dust, so the dust mass loss rates are going to be 100 or 200 times higher. Results we can get. Now to the question, why have I not started with talking about what we do in our own galaxy? Well, the main problem is the foreground extinction. For the near objects, even for these nearest objects, the Gaia parallaxes the uncertainties are huge. And so I'm not sure how many of you are aware of the Gaia study, but Gaia parallaxes for main sequence stars have precisions of the order of 10 to the minus 3%. Right? There are many problems with evolved stars that cause this issue, even for the nearest objects. One of them is that these stars are pulsating, so it's much more difficult to get a distance parallax without accounting for the proper pulsation as well. The other reason is, of course, these stars have dust around them, and Gaia is an optical survey. If you have a dusty star, it's not going to be very bright in the optical. So that also kind of gets in the way. This means that we don't really know very well what the distances to these stars are with a high precision. If you don't know the distance, you don't know the luminosity. You don't know the total dust. Though these stars are so close to us, for the past 100 years, we don't really know the distance of these objects. I mean, that one is, Mira is the nearest star to us. But is it though? Because that's a 10% uncertainty, and this one is also 90 parsec, that's 20% uncertainty. So this is one of the problems this is the problem we're having at the moment. Gaia has had 3 releases so far. The 4th release will probably have enough data that it could account for the convection processes, the pulsation processes, and reduce the uncertainty in the parallaxes for these objects, and then we should be fine. But in the meantime, what we can do is, I showed you this plot of the distribution of luminosities for AGB stars from the Magellanic Clouds. We can use that to get an idea of the typical luminosity of an AGB star, and then assume that all the stars have that exact same luminosity, and then use that and the spectral energy distribution to calculate the distances. This is similar to what is done in cosmology. This is luminosity distances, basically. So the only difference here compared to what previous studies have done is we have not only an average value but also an uncertainty around it. We can do a 50% confidence interval around this. And it turns out, so a 50% confidence interval in luminosity is a 25% in uncertainty in distance. 25% seems like a lot, but for most of these objects, even the best methods of estimation, alternate methods of estimation, give you uncertainties higher than that. So 25% is the best we can do right now. So we started with that. We have an approximate idea now of where these stars are. Now we want to study the nearest stars. So now that we can define how far they are, we can isolate the nearest ones. That's where our study comes in. So I'll try to quickly run through this. Let's see, what time? Yeah, okay. I'll run through this quickly. Just tell you a little bit about what the study actually is doing, so that I can jump to the results. So the idea is we wanted to have a large enough sample of nearby stars. So of course people have been observing individual objects for the longest time. They've been done to death. We've been looking at the same 10 objects over and over again. But this does not give you anything statistical. You may know everything you want to know about the sun, but unless you know how typical the sun is, you're not going to make any more judgments about the stars around you. So we wanted a large enough sample, and for this large enough sample we wanted to study what is the total rate at which gas and dust is being returned to the interstellar medium, and also what is the distribution of mass loss, what is the mass loss history of these stars. And because if you have a large enough sample, you can do this in a statistical sense. So that's the main idea of how does mass loss evolve as the star evolves, and what is the distribution of mass losses you get, what is the history of this mass loss. There are a lot of other science goals that you can look at, which I'll talk about a few of these in detail. But the basic idea is this: have a large enough sample, get the mass loss. Talk about the mass loss history. And our data, we started with, and I mentioned the different wavelengths at which you can study these stars. We started with sub-millimeter and radio information, which is where you look at rotational line transitions of molecules, specifically the carbon monoxide rotational transitions. That will tell you a little bit about the distribution of gas in the shells. We can combine this with mid-infrared observations, which tell you about the dust. And the three main pillars of our survey is, of course, statistics. We want to do something statistical. We want to report the results, but also with uncertainties. We want to be reproducible. If we do something, we make sure that you never have to do it again. That's the whole idea. Or if you want to do it, to make sure that we're not lying or fabricating something, you should be able to. That the philosophy of reproducibility is something we take very seriously. And of course, related to it, open science. We make our code base, our raw data, process data available. In principle, every paper that is published comes with a Python script, which if you run it, it will download the raw data for you from some public archive, process the data on your machine, and then produce all the plots that are in the paper, and then produce the paper itself. So that if you wanted to, you could verify whether we have done what we actually say we do. And so there was a meeting last May which talked about reproducibility in open science. If you follow that link, or if you just look up ROSA 2022, the talks are on YouTube, and they're extremely interesting for anyone who's even slightly interested in data, reproducibility, and open science. They talk about a lot of utilities that astronomers and scientists can in general use to stay reproducible and to adhere to open science. Especially for younger scientists, this is a big deal. My generation is already lost, but there may be hope with you all. So we select our sample from a large database of mid-infrared objects. Now that we have a way of estimating the distances, we get about 800 objects, and then where available, if there are other studies that have better precision in their distances, we use those distances. We have about 850 objects here, for which, once you have these spectral energy distributions, we can estimate what the dust production rates are with some models that we have. And we've done that, and these two plots basically showing the dust production rate as a function of distance. So there are 5 different tiers of these objects. The nearest objects, we can go to very, very low dust production rates because we can study fainter objects, intrinsically fainter objects at smaller distances. At the largest distances, we can only look at the brightest objects. So that's why these are the most highest mass losing objects here. This plot over here, this candlestick plot, shows a distribution of the total dust production rate in each of these tiers. And surprise, surprise, the most mass losing objects, even though there's only a handful of them here, contribute most to the total dust budget. The sample that we have is actually an improvement of up to a factor of 5 at distances above 500 parsec or so. This is something hugely significant because the statistics involved, the precision with which we can make our claims is much higher than what other studies have done. We have observations from a huge number of facilities. We started with the James Clerk Maxwell Telescope. We have rotational transitions of carbon monoxide. We added other surveys. So APEX is the Atacama Pathfinder Experiment, which is a radio telescope. Nobeama is a radio telescope as well. IRAM as well is an interferometric radio telescope. And we just recently also scored some time with the Large Millimeter Telescope in Mexico, which is also radio. We have a huge amount of data, way more than we can handle, and this is one of the reasons we need help. We have lots of archival data as well. This is all publicly available archives for which we have codes, and we would like people to create codes to access this data publicly automatically so that people don't have to do stuff by hand. And this is one of the reasons that we're asking for help as well. Okay, running quickly to the first results from this survey. So one of the very first studies was, I said how we wanted to look at the mass loss history in these objects, trying to look at what is the distribution of, is the rate at which the dust is lost, is that constant? Is that, is there a constant distribution, or is it in phases? Are there puffs of material? Well, in some cases, such as Uantlier, which is a nearby star, this star is about 500 parsecs, 3 to 500 parsecs away from us. This is the spectral energy distribution. That's the flux as a function of wavelength. This is 1 micron, so that's the near infrared. You can see that the star peaks in this. This is the optical wavelength range. That's the mid-infrared here, and then this is the far infrared and sub-millimeter. And these are the individual observations that we have, and then the two curves are models that we have fit to it. You notice that first, in the optical you have all of this stuff happening. That's the line blanketing I was talking about. These are molecular absorption bands that are so close to each other and so deep that the optical basically vanishes. And then you go to the near infrared where the actual star's emission peaks. Beyond that, you have a little bit of dust here. It's difficult to see in this plot. A little bit of dust in the mid-infrared. But then there's a sudden bump here. That is a detached shell of dust. This is something where, so this star is an example of a phase in the star's lifetime where at present the dust production has stopped. So there's no dust here. That's why the shape of this thing looks exactly like a naked star. At longer wavelengths, which means, remember, this is colder dust, and therefore older dust. Longer wavelengths, you have this bump. So a few thousand years ago, there was dust production. And that has resulted, and that dust moved away from the star. And that's what this thing is. So this is called a detached shell. I'm sorry, I should have put an image there, but what it looks like is basically you have the star in the middle, and then you have this ring around it at about 54 arcsecond or so. The time scale for that turns out, so this puff of dust was created approximately 100,000, 10 to 100,000 years ago. And again, because of the wavelength at which the peak is, because of the flux level, you can actually work this out. And the speed at which this dust is expanding, you can work out what the time scale should have been. What we've done here is we've taken for each of these, let's see, 10, 100, okay, these measurements here, these are the far infrared and sub-millimeter measurements. We've taken those, we've actually mapped them out at each radius from the star. This is radius in arcseconds, so this is the angular distance from the center of the star. We have this map. So this one is the 70 micron plot. That's 160, 450, 850. The 850 micron plot shows that it decreases initially and then just kind of flattens out. What you expect if the star only had this detached shell is you initially expect a little bump where the detached shell is, and then beyond that you kind of expect the flux to just die out. As in, there's no more dust beyond that point. What we're seeing here in the 850 micron is there's way more dust beyond what we can see, what we have seen in previous data. So this means this is actually already telling us that there is mass loss that has not been measured previously that we're looking at. This is the oldest mass loss. This is hundreds of thousands of years in the past, the original phase of mass loss that it started. And this was the very first NEST paper. This one actually includes with it the code that can generate the entire thing. Subsequently, in other data, we have also discovered other stars that have similar excess emission as well. Let's see, how much time do I have? That's about 15 minutes or so, maybe 10 minutes. Yeah. Okay, all right. Yeah. I'll skip that. Let's see. Oh, yeah, I'll look at that. So I talked about the dust. Now I'm going to talk about the gas here. This one is basically the same thing I showed you for the dust, which was that the dust emission extends well beyond what we thought. This is the same thing, but for the gas. So this plot here shows, excuse me, basically a number that's proportional to the flux of the gas emission as a function of distance from the star. You can see again, it peaks at about 15 or so arc second, but beyond that, it doesn't immediately fall off. It actually tapers out to at least about 40 arc seconds. So that again tells us that there is extended emission in the gas as well as the dust. So our first results show that the intention we had of mapping the mass loss history in these objects is actually feasible. So this is only, we've only looked at so far, processed maybe 10% of the data. And we have way more to do, many more projects to actually work through, and we don't have enough people. So again, we need help. So this is again the first demonstration of our what we intended to do, where at least we have results that, okay, well, this is exactly what we expected, so that's great. I'm going to skip that. Yeah, one of the other things you can do, so Rahul's question was about oxygen and carbon specifically, but I kind of took that into the R process and S process. So carbon-12 is an S process element. It's actually created in the nucleosynthesis from AGB stars. Carbon-13, however, is an R process element. So the ratio of carbon-12 to carbon-13, the isotopic ratio of carbon, can actually tell you something about the evolutionary stage of the AGB star. The larger the ratio of 12 to 13, the more evolved the star should be in general, because carbon-12 is only generated and transported during the AGB phase. So one of my students took whatever data we had and has produced plots of the 12 to 13 ratio for all our sources. So we see that there's a huge range actually, and this actually shows that we have a range of evolutionary stages in the carbon stars in our sample. This is again very, very preliminary, so we're still working on this, but it's one of the interesting things we want to look at, because that kind of tells you what fraction of your stars are in the most evolved stage, and that those most evolved stars are going to be the ones producing the most dust at this point of time. Another thing you can do is, there's the chemistry of these objects. It's different, carbon-rich, oxygen-rich. You can use machine learning, and again, there's so much data we have that there's so many of these projects possible. This is only one small example of what you can do. Because we look at color magnitude diagrams, color diagrams, and most of the time we only have that information, we have to draw some arbitrary boundaries in the space and decide something to the left is a carbon star and something to the right is an oxygen-rich AGB star. You can do something slightly more advanced by taking all of the points in the spectral energy distribution, dumping that into a machine learning code, and have it classify as well. So what I'm showing here is results from another master's student that I have who considered a different set of classifying algorithms to do this. He finds basically he gets about 88% true positive rate on separating the carbon stars from the oxygen-rich stars. For our sample, this is actually very, very good. If it was the Magellanic Cloud sample, you'd get an accuracy of 95% or more, because the data there are much better organized and they're at the same distance. In our case, because this is a galactic sample and we have all these uncertainties, 88% is not bad at all. Skip that, skipping that. So this is another thing that we can do with archival data. So we need spectral energy distributions for all these stars. We have 850 stars. We have 24 surveys at different wavelengths that we have to collect data from. They're all available online, but they all have their own missions and quests that they send you through, trying to force you to be not automated. So one of my students actually just struggled through this and has generated Python code that will now allow you to automatically access the SED of each star as well. This is something that I encourage young scientists to do, turn everything into, so now, at least in astronomy, you have most of the databases are automated so that you can run Python queries in the command line and get all the data that you need without ever having to go to a website and actually typing in things like you're in the 1900s. So this is another thing that I actually encourage people to do. There's so much data we have. We can also collect light curves for these objects because they are variable sources. Pinaki's question is about how can you tell what the pulsations look like. Well, we have light curves for these objects in the optical, the near infrared, and sometimes in the mid infrared as well. And one of my students right now, master students, is collecting data from, this is only I think 2/3 of the archives that he's collecting data from. So there's a huge amount of data that he's collected and then analyzing using a Gaussian process fitter to fit the light curves. And these are some examples of fits that he's gotten. So you can get a period estimate out for these objects and of course uncertainties on the light curves as well. Yeah, astronomers are horrible and they're still stuck to their old methods. I did a Facebook survey last year or the year before and yeah, it turns out most people are still doing stuff by hand. I don't know if most of this stuff is probably alien to you, but ADQL is the completely automated version of SQL that you can run through Python. And unfortunately, most scientists do not use ADQL. They go to the website, type in the float coordinates of the object, and then proceed from there. We're trying to just change this. Okay, so I'm going to really wrap things up here.
Because this actually crops up in other fields also for,
is there a standardized ontology or the table headers, field names, the things like that? Those should also be.
Yes.
So in astronomy, you have standard ways to present this information so that.
Yes.
Okay.
So Simbad, which is system of identifiers, main, blah, 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 and Vizier, which are both from the CDS in Strasbourg. These are databases maintained and have existed for at least 30 years that have all of this information, and they make information available on how to efficiently access them. So the idea is that if anyone has ever studied an object, whether it's a star or a cloud or whatever, you give it a unique identifier. And then from then on, subsequently, instead of referring to the float coordinates, whose precision changes every time you improve your telescope, you refer using the identifier. And then what they do is, of course, multiple people might have the same name for this, different names for the same source. They tag them all together. So they also have tables where you can just go search, give me all the names for this particular source. Completely automated. So yeah, there are ways to do this. Yeah, we can talk later if you like. Yeah.
Thanks.
Sure. Okay, so the summary of what I've been trying to tell you is, well, before the summary, yes. So why do we need India? Well, yeah, like I mentioned, we used to have access to the JCMT, the James Clerk Maxwell Telescope. Our access is dwindling because the scientists who work in countries that have access to the JCMT are moving out and going to other places like Mexico. So we need JCMT time. And we have ongoing proposals, but very soon that will run dry. So one of the reasons we need Indian scientists to work with us is that so that we can increase our collaboration to include other countries that still have access to JCMT time, which allows us to continue our follow-up observations. I had a rough idea with a couple of my collaborators about what science we could do with the GMRT. One idea is to look at atomic hydrogen emission. Now the difference is that with molecular hydrogen, you're not directly looking at the molecular hydrogen. You're looking at the carbon monoxide, the rotational lines of carbon monoxide, which are excited by collisions with molecular hydrogen. Then you have this imaginary factor, not imaginary, but really imprecise factor, the CO2H2 ratio, which you use to convert to figure out the mass of hydrogen that's involved in this molecular hydrogen. Instead, if you use H1 emission, you're actually directly looking at the thing that's responsible for this emission. The inner regions of the stars have effective temperatures greater than about 2400, 2500 Kelvin or so, are entirely H1 dominated rather than molecular hydrogen dominated, which means in these cases you can trace the entire circumstellar shell all the way from the dust formation zone out to the place where it intersects with the ISM. This means you can study the entire mass loss history up to a couple parsec or so. I checked the GMRT archive and I've only found one study that was for, I think, 2006 or 2008, which had looked at a handful of sources, nearby sources for H1 emission, but there's no publications associated with this work. It was curious that there were 3 sources that overlap with the, we have NEST sources in there as well, so I would be very curious to see what they found. We know that there is some existing work for a handful of nearby objects done with the telescopes associated with IRAM, where they have looked at the H1 emission, and I think the main reason they didn't go any further is because they're waiting for the NGVLA. Based on what I've read about the UGMRT, I think the UGMRT is sensitive enough that we can do this while we wait for the NGVLA. So this is another thing that I would love to talk to Indian scientists about. I think we can definitely do this while we wait and get some publications out. India also has access to optical and near-infrared facilities with which, so because of the atomic lines and molecular bands, we can actually use the optical and near-infrared spectroscopy to figure out what the metallicity, or the, like I said, the fraction of heavier elements is in these stars as well. And the metallicity of the stars will tell us a little bit about the chemistry as well. So that would also be an important thing to do. So yeah, these are just some ideas I had, but if anyone would like to talk to me about this, I'd be very happy to do that. All right, I'm gonna finish up here. So our idea was to study the total mass return to the solar neighborhood, about 3 kiloparsecs within the solar neighborhood, and get a large enough sample with which you can do this. This data will be completely public as soon as every paper is published. Our overview paper has already been published. You can take a look at that. We have a catalog. The catalog is available on the website, which I'll flash on the next slide. And we have so much data, we don't know what to do with it. Students, especially if you're interested in remote work, come talk to me. There's so many things we can do. And that should say masters and not majors. I don't know why that says that. We have majors too. Yes, so just something I said just now is that we have other projects we have ideas for, but again, we need contributions from scientists from other regions as well. So evolvestars.space is our website. You can go there, check out the, if you're interested, you can go to the members page and just say I want to join, or you can check out the catalog itself. The interface is such that it allows you some basic search capabilities, but also just gives you an idea of the kind of data we have so far put up online. And there's going to be many, many more things up online over the next decade or so. So thank you very much for giving me this opportunity, and please let me know if you have any questions. Thanks a lot.
Thanks, Sundar, for this very interesting talk where we definitely learned something. Yeah. Questions? Yeah, Dheeraj.
Nice talk. I just checked that there was a model called COMAX model, if I'm pronouncing correctly. Okay. What was that model and why doesn't it produce this thing? I mean, these anomalies, of course, you have explained those anomalies. So that model doesn't take into account the dust.
COMARCS stands for Copenhagen opacities, and MARCS is the model atmosphere, I forget what RCS is. Those are the models for the photosphere itself. They include only the photosphere and the opacities for the gas, but not the dust. So it's only the star plus the gas. So they reproduce the optical for stars that don't have dust. But I mentioned another thing called GRAMS somewhere in here. GRAMS is the grid of red supergiant and AGB models, which takes the COMARCS models and adds dust around them and calculates the radiative transfer.
So that one is the other one that was fitting well the data.
Yes. So that's something that we came up with. Let me move back to that one there. Yeah. So yes, the wavy stuff you see, that's the COMARCS model. So it does a good job of reproducing the optical and the near-infrared here, because this star does not have warm dust. In that case, there's no interference. At the longer wavelengths, the Comax model this is just an extrapolation because they don't have any dust. What we've just taken the Comax model as input and added dust around it and calculated the radial transfer.
And what are the three SS1, 2, 3?
So yes,
three different
so those are different models for how the dust is distributed in this particular star. Depending on who you ask, in the optical, some authors said they saw 4 shells. That's the SS4, subshell 4. Some people said they saw 3 shells, some said 2, some said 1. So we said, let's take all those into account, produce models for each of them. And what we're showing here is that regardless of what you pick, basically like, except for this one model, which is the SS3, the other models are able to reproduce the observations.
Okay, so that means that the one shell model, right, MSS1 that you said, that is not fitting well. So there is no free parameter that tunes the amplitude. So it is just a fixed thing that you plot on top of that.
So this is the subshell part is just based on observations. Yeah.
Okay.
Yeah.
Thanks.
Sure.
Any more questions? Yeah, Shantanu.
So for getting results here, so how much observation do you need to get the errors under control? So like for these kind of plots.
Right. Let's see. The AGB stars are very, very bright, so the photometry itself, it takes a minute or so.
Okay.
In most of these cases. So the near infrared, for example, I remember looking at Magellanic Cloud stars, it takes less than a minute. So the galactic sources that are much nearer to us, it's not going to be a lot of time at all. Yeah. It's only the spectroscopy and the emission lines that take a bit longer. Yeah.
Mm-hmm. And you didn't talk about the other route of getting this dusts or this AGNs from this neutron star thing.
From supernovae, yes.
Yeah, supernovae.
Because the problem is that the dust destruction rate is uncertain. What is the magnitude? So they don't know what fraction of the dust is destroyed. The estimates go from 10% to 100% basically.
And why is it so?
It has to do with how the radiation, so how strong the radiation is and how much shattering of the dust particles there is. So dust evolution models say that you have to have a certain, I don't know very much about this, but you have to have a certain minimum grain size in order for dust growth to progress. And it's not entirely clear. So basically, observational data wise, what we need reverse shocks. Reverse shocks is where the dust get destroyed. But observationally, we only have, I think we have 0 sources known where the reverse shocks are. So 1987A is the most famous thing. And there is a paper from 2011, Mikako Matsura, which says that they've discovered up to a solar mass of dust in 1987A. Even if you disregard the modeling issues here, the problem is that it's still in the pre-reverse shock phase. So the dust has been created, but after the reverse shock, it's going to be destroyed. And we don't know how much of it because of the way the shattering works and the way that, I think there's also a difference between whether it happens spherically symmetrically or not.
Yeah. Thanks.
From optical to near infrared, all the data points are consistently lower than the projected predictions. Is there a concern or?
No, not really. At this, so the, let's see. The uncertainties are large enough in the photometry that it's basically consistent there. Yeah, that's, it could just be normalization in the distance. That's so that one, for example, there, right? So in this case, the error bars are large enough that I think. So there's 2 things. There's one part of it is that there was already some model and systematic uncertainty in the modeling that we assumed that we could not control.
Yeah.
I think that part of that is causing the problem because it has to do with how we converted back from the radial profiles back to the SED, and there's some uncertainty that I forget from. This is we were working on this in 2018. There was some uncertainty there that we just didn't have time to address. Okay. So part of it might be just a calibration issue.
Yeah. No, actually, I was not worried about the only one point.
I
One point.
understand.
It is within 2
It's an
sigma error
absolute-
bars. I'm not worried
Yeah.
because since all of the points are down, so I was just
So,
thinking that if you bin the points,
So I think it's an
it might be 3 to 4,
Oh.
4 to 5 sigma.
Right.
You cannot bin the points. I understand.
Yeah. No, what we do is so in order to actually compare the spectra to the points, we convolve them through the broadband filters, the same broadband filters which these photometry points were generated in.
Okay.
Right? We haven't done that. If we do that, then yes, we'll be able to absolutely calibrate it.
Matching will be much better. Okay, thanks.
It must be really challenging to work over this huge range of wavelengths, and from optical to radio. So my question is, what are some of the major challenges that you might have faced to combine this multi-wavelength data? And the second question is, how really can the UGMRT help?
Yeah. Well, all right. I'll attack the first question because that's easier. The main challenge is that these sources are much more variable in the optical than they are in the mid-infrared, because the optical, the reason the amplitude in the optical is very high is because titanium oxide lines are, titanium dioxide is extremely sensitive to the effective temperature of the star. So the absorption just dips suddenly if the effective temperature changes by 50 Kelvin or so. So the amplitude here is going to be huge. And so what you really need is simultaneous observations across all wavelengths. If not, then this might have been observed at a different variability phase than this one. And so the main issue comes here. Of course, beyond this, the amplitudes are not very large, so you can basically say that's the SED. As far as I'm concerned, that's my main irritating, also because here, even though the Comax models take into account some of the opacities, they aren't yet completely there yet. In fact, because they run out of computing power. This is another issue that is very irritating. So what we need is better models for the optical, and also kind of variability averaged SEDs in that region. In the sub-millimeter, an issue is mainly the issue is with the beam size, because you actually start resolving these stars. So then in order to actually put this point on the SED, you need to integrate, but the thing is, everything else, it's unresolved. So that becomes an issue as well. Yeah. And your question was, how do I use the GMRTs? Yeah, well, that's why I came here, talk to you people. So the only thing that I looked up was, for this H1 emission thing, I just wanted to see if somebody had done something similar. And there was one study that I looked at the archive and just said, just the title said H1 emission from AGB stars, and they mentioned which sources they were. But that's all I know, because I can't access anything else. So we thought about it, and it seems like this other group has had, with the non-say array, has done, they have 5 or 6 papers or so, where they've looked at the feasibility of this for a few nearby sources. I believe, and this belief is just based on the bare minimum I've read from the GMRT website, that the UGMRT has sensitivity higher than what they have right now. And we're at the right time before the NGVLA that this might be done. If we, I mean, we have the stars, we know where to look, we have data for these things, so it's just a matter of getting some experts in there and filling the blanks. Thanks for the question.
Any more questions? I have a very naive question. So you do radial, you're showing. So how correct is it to do radial? I mean, in the sense that you can have heterogeneities and so on.
Yes, exactly. Yes, so that is, we are looking into that. So this was a first, this was a, even in the images for the star, we know that it's not spherically symmetric, right? So in a way, when you're doing a radial profile, you're basically averaging over, and that's what these uncertainties here, they take into account the fact that you're averaging. So you have some knowledge of the non-spherically symmetric part of this distribution. The next step of this is to do a 2D version of this. Yeah, so it's in the works.
And can one backwork and figure out what are the transport processes that has led to this kind of structures and so?
Yes and no. So it's much easier to do forward modeling and then do like something Bayesian. So you just figure out what, put in whatever component you want, you produce a model, convolve it through the filters, and then compare it with observations. The other way around is much more difficult.
Okay, I think that was a very fascinating discussion. So thanks, Sundar, for
Thanks a lot.
visiting and giving this exposure to this very beautiful world. And we end today, and I think there is coffee and snacks outside. So thank you.
Thanks.